Hello and welcome to my predictive model of the NASA budget. The NASA budget is only a third of a percent of the total federal budget. That means for each tax dollar spent, not even a penny is going to NASA. Which is sad because NASA is responsible for bringing humanity to the moon, both in 1969 and 2026 with the Artemis program. They also cemented our place in space with reusable spaceships and the creation of the International Space Station. And finally, they developed everyday technologies like phone cameras, memory foam pillows, shoe inserts, and even cordless tools like power drills and vacuums. I've always had a love for science, and when I was young, I went to the Kennedy Space Center, and I was, in the most literal definition of the word, awestruck by just what we could accomplish in the field of aerospace. But sadly, in recent years, NASA has been struggling to get a reasonable budget. Thankfully, there are people who share my love for NASA and work to help it. For instance, the Penny for NASA movement in 2012 that sought to raise NASA's budget to 1%, originally inspired by Neil deGrasse Tyson's speech in Congress and founded by John Zeller. Additionally, there was the Saving NASA Science movement, a more recent one that wanted to stop the potential slashes of 46% and up to the already infinitesimally small NASA budget. This presentation will show what political and economic factors statistically affect the NASA budget, perform regressive analysis using a time series regressive model, and a modified version with ARIMA, and finally develop a predictive model using R to forecast values with ARIMA. I will start by discussing my methodology, then I will show my results, and finally I will discuss what can be learned from these results. The potential economic variables I will include are federal net outlays because if overall spending increases, it makes sense the national budget will have a correlated effect. Then I will use the gross domestic product percent change because if the entire country makes more money and once again makes more sense that it will have an effect on the NASA budget since the economy is doing better. Next will be unemployment rate, which indicates how badly the economy was doing and broadly the well-being of the populace. Finally, I will use inflation, which is a dependent variable that represents the cost of living and the overall state of the market. The political variables I consider are mostly binary, which means they will have values of 0 and 1 to denote a certain condition, such as the space race. The first two variables, the party of the president and overall unification of the government, have obvious importance. The space race is responsible for the biggest spikes in the NASA budget throughout history. And finally, the last one measures overall military spending and is important to document any time of war or other high conflict time period. The model I will be using is a time series regression model. The purpose of which is to model the linear relationship between the NASA budget and the various predictor variables I just discussed. This will allow me to see what ones have a statistical effect on the budget and maybe predict future values. Each variable's value is mapped to a year from 1958 to 2025, hence the name a time series. This model is multiple linear regression because there are multiple predictors. According to forecasting principles and practice, this is the general equation. The beta terms measure the effect of each predictor after taking into account the effects of all other predictors in the model. The error term does not imply a mistake, but a deviation from the underlying straight line of the model that fits to the data. It captures anything that may affect the forecasts or the predictors. The T subscript indicates it's a time series. The model has some underlying assumptions that allow it to function. Some are more necessary than others, but all are pretty important. The relationship between the forecast and the predictors has to be roughly linear, or else we have to introduce some nonlinear formulas. There are no outliers or influential observations to throw off the variance of the model. There is no correlation between predictor variables, so that the statistical performance of any one of them is overinflated or underinflated, and each predictor X is not a random variable and is controlled in some way. Residuals, as defined by Gareth James, are the difference between the ith observed response variable and the ith value that is predicted by our linear model. The residuals have the underlying assumptions of having zero mean, otherwise the forecast will be systemically biased. They are not autocorrelated, otherwise the forecast will be insufficient and more data would be needed. They are normally distributed and have constant variance, which are useful for producing prediction intervals. To evaluate my model, I will measure the Keynes information criterion, the corrected version, which is basically a measure of how accurate the prediction is, and I will use different variations of the model showing which combination of the variables minimizes it. In addition, I will use code such as the report function to provide a summary of important facts, like p-values, which show this how significant each variable is on the NASA budget, and the coefficient of determination, r squared, which measures how much variation there is and in the difference between the fitted values and the regular model. I will use various plots and coding functions to check my residual assumptions, such as an ACF plot and a Lejeune box test for autocorrelation, a histogram of residuals to check for a normal distribution, a residual plots against predictors to find any relationship between them, to see if there's like a linear relationship, for example, and others such as a time plot and a plot of residuals against fitted values to check for that the variance is constant. I will check the variable assumptions using similar methods, such as graphing each predictor against the budget to make sure that the relationship is linear, and finding the correlation coefficients for each variable. There are various ways to deal with outliers and influential observations. One I tried to employ was creating a dummy variable in the space race to counter the massive spikes that was caused by that time period. Because the values are in their historical ranges, outliers are not necessarily so much of an issue as they would be in other situations. Forecasting with regression will involve me modifying the formula by introducing ARIMA errors. In this new model, there are two error terms, the error for the regression model and the error for the ARIMA model. This forecasting with this model has the benefits of addressing autocorrelation and predicting future values of the budget more accurately by including the dynamics of a time series. In addition, I will use a Cox transformation on the budget as a percentage of GDP because this deals with non-constant variance, and forecasts will no longer result in negative values, such as a negative budget. The ARIMA assumptions are basically that they have stationary variables, which means their properties do not depend on the time in which the series is observed, and they have no predictable patterns in the long term. And second, ARIMA errors model white noise, which means that the ARIMA residuals have to follow the assumptions I already explained beforehand, and they will be tested in the same ways, like ACF plot and a Lejeune box test for autocorrelation. Box-Cox transformations can help solve some of the issues caused by outliers and other things. I will calculate the lambda for the NASA budget, which can be used to either apply a power or a log-based transformation. It will most likely be a power since the lambda I calculated was not zero. I will transform it using the box function, as you can see on the data on my right in the final version of the ARIMA regression model. Here are the R packages that I used imported from the FPP3 package. Most notably, RStudio is particularly useful as that's the platform where I did all my coding. This scatterplot matrix shows the various predictor versus forecast variable graphs and the correlation coefficients for each variable. The first column shows the graphs between each predictor and the NASA budget. And as you can see, some of them have a clear linear trend, such as the military spending and the NASA budget one. The upper half of the graph shows the correlation coefficient, and since none of them are too close to -1 or +1, there's not a real sign of multicollinearity. The main diagonal shows a density plot, and they're not really relevant for this presentation. Here are the predictors that I found to be statistically relevant for each model. And I did this by finding the collection of variables that would produce the smallest AICC value for each model. The results of my residual test returned some negative results. For example, the Lejeune-Box test showed that their residuals are correlated because it had an exceptionally small p-value. The mean was practically zero, which was good for the residuals. However, there are definitively a few outliers, as you can see in the time plot and the ACF near the beginning. The histogram shows a roughly normal bell curve, but once again, there are a few outliers. It looks like there's some pattern in the residuals versus fitted scatter plot, which means the variance is not constant, and the box plot transformation for the NASA budget is probably needed. Additionally, there seems to be some patterns in the residuals versus predictors graphs. While some, like the top row, seem to be random, military and spending seems to have perhaps a non-linear thing. This is why ARIMA errors are probably a better model fit. The ARIMA modeling results are significantly better, such as the residual time series resembling a white noise series much more, and the histogram better resembles a normal bell curve, and the Lejeune-Box test has a p-value much, much larger, which means they are not autocorrelated, and even some of the outliers are not as extreme. The important stuff to pay attention to here, besides the estimated correlation coefficients, are the AICC values, the adjusted R-squared, and the p-values. As you can see, the AICC value of the regular linear regression model is almost half of that of the one with the ARIMA errors, meaning the one with the ARIMA errors is an overall better fit. The p-values show the significance of each of the variables. Roughly speaking, the more stars they have and the lower they are, the more significant that variable is. And finally, there's the adjusted R-squared. This shows the total amount of variation between the real values and the fitted ones. Since it's only about half or 50%, that means only half the variation is explained. On this slide, you can see the fitted versus actual values compared for both models. As you can see, the regression with ARIMA is the overall better fit for various reasons, such as its residuals better matching the requirements and a white noise series, and having constant variance. Here are the final versions of the regression equations for the regression with ARIMA errors and the linear regression equation. Each one is different in its own ways. For instance, military spending has different correlation effects for the NASA budget. Each correlation coefficient represents the change in the NASA budget for each 1% change. For instance, a 1% increase in military spending would mean a 0.19% increase in the NASA budget for the linear regression equation. Finally, here's the forecast graph for the next 8 years for the NASA budget. As you can see, there seems to be a slight upward trend, perhaps even reaching 1%, as can be seen in the 95% confidence interval. The blue line is the average of all predicted values. A similar study to mine was done in 2013 by a man named Smiley. My model measures percentage of the national federal budget. He measures NASA budget in millions of dollars, so they're not one-to-one. We had measured similar factors, and they had similar significant effects, such as the political party. However, military spending had the opposite effect. Interestingly, the space race was not significant in my model, and I further expanded mine by introducing ARIMA errors and forecasting. My model has many limitations. For instance, there are many more variables, political and economic, that go into deciding the final version of the budget. and I'm using the historical means for the future values of military spending and federal net outlays. But overall, the forecast looks positive, possibly even 1%. And 1 penny of your tax dollar would make the sky only a limit for the future of human aerospace. Here are the references that I used in my presentation and developing my model.